Let's imagine that we have a number like this, 1670000. To write this in scientific notation, we first write the digit that's farthest to the left, the farthest to the left non-zero digit, so in this case 1. And then, if we have more significant figures, if there's only one sig fig, then we just have one digit and we do not need to write the decimal point. But if we have more significant figures, we put in a decimal point, and then we follow it with all of the other significant figures. Now, in this case, if we only have these two, 6, 7, we write this as 6, 7. But 1.67 is obviously not the same size as 167. What is this? That would be 1,670,000. So to make this as big as this, we multiply by a power of 10. Now, what power of 10 do we have to use? Well, what we're going to do is imagine the 0 starting here, 1.67. How far would we have to move it back to get it to the original position where it would be over here? We'd move it 1, 2, 3, 4, 5, 6 places. So we say 1.67 times 10 to the 6th. And then this is this number, but written in scientific notation. What if we have a very small number? For example, let's imagine we have 0.00053. Well, again, we write the first digit on the left, the first non-zero digit, which in this case would be 5, followed by a decimal point, and then all of the other significant figures, in this case 3. And then we multiply by a factor of 10 to bring this back to the same size. Now, how much would we have to move it in this case? Well, in this case, we would have to move it, if this were 5.3, we'd have to move it to the left. So we're making it a smaller number in this case. So 1, 2, 3, 4. So we would multiply this by 10 to the negative 4. A very general rule of thumb that I want you to keep in mind, because we're going to be seeing this over and over again. Numbers with positive exponents, when something is written in scientific notation, numbers with positive powers of 10, big numbers. Numbers with negative powers of 10, small numbers. Joe, just keep that in mind. Positive powers of 10, big numbers. Negative powers of 10, small numbers. Okay? Great. Sometimes it's important to write numbers in scientific notation to emphasize exactly how many significant figures that number has. For example, if you have some measurement or some number that has come about from a calculation or something, let's say we've got a number like this, 12 million. But for some reason, perhaps you know that we really want those two zeros to be significant. Maybe those two zeros really are significant, whereas those 4 are not. Well, if we were to just write it like this, that would indicate that we only had 2 sig figs. Now, how could we write this number and emphasize that it had 4 significant figures? Well, some people say, well, you can underline them or something like that. What I would suggest, and what we will do in this class, is write it in scientific notation. So what would it be? 1.2, but then all of the significant figures would include 0, 0. So we'll put 1.200 and then times 10. Well, this is a big number, so we're going to have a positive power of 10, right? So how many places do we have to move it? So from 1.2, we move it 1, 2, 3, 4, 5, 6, 7. So we have to move it 7 places, positive 7. So 7. Now you could put plus 7 in there if you want, but the plus is understood if you just write 7. So we can write this 1.200 times 10 to the 7th to indicate, first of all, in scientific notation, this number, but to emphasize that it has 4 significant figures in this case. Keep in mind, when a number is correctly written in scientific notation, all of the digits written will be significant. So, in this case, 1, 2, 3, 4. If the number is in scientific notation, whatever the digits are here, zeros, wherever they are, it's going to be significant. That first digit is never a 0 when it is correctly written in scientific notation. Okay, now, how do we combine numbers? algebraically, arithmetically. How do we combine numbers arithmetically, like plus, minus, multiplication, division, emphasizing the correct number of significant figures? Well, let's take a look at that. Let's imagine that we want to multiply 2.23 times 5.8943. If you just plug this into your calculator, what you'll get is 13.144289. My question is, can we really quote all of these significant figures? Is it really appropriate, knowing what we know about how uncertain we are about these two values? Well, what do I mean by that? Let's keep in mind that when we say, or when we write 2.23, typically we're really talking about some approximate value that could be as small as 2.225, this value minus 0.005, or as large as 2.235. While this number could be as small as 5.89425, or as large as 5.435. So the product could have a value that's as small as the product of these smaller values, which turns out to be 13.11470,625. Or the product could be as large as the product of these two larger values, which turns out to be 13.173872225. So what can we really say about the product that we're looking for? Well, can we really say it's 13? Well, it could be as small as 13 or as big as 13, so yeah, we can say the product is 13, at least 13. Can we say 13.1? Well, yeah, this is as small as 13.1 or as big as 13.1, so yeah, it's fair to say 13.1. Can we say the value is 13.14? Well, the value could be as small as 13.11 or as large as 13.17. So can we really say the value is 13.14? No, we can't. The best that we can say is that the value, and I'll put this in parentheses here to emphasize that that's not really what we're going to say here, we will say the value is 13.1. That's really as precise as we can be with the uncertainty that we are assuming with these values. Therefore, this kind of shows us, gives us an idea of where we're going to go with this. I haven't proved this, obviously, for any case, but there's a very general rule of thumb that we will be using this kind of indicates. How many significant figures, let me get rid of these first, sorry. How many significant figures does 2.23 have? 1, 2, 3. That's 3 sig figs. What about 5.8943? 1, 2, 3, 4, 5. Has 5 sig figs. How many significant figures can we keep in our answer? Well, 13.1, we can keep 3. The general rule of thumb is when you are multiplying numbers, and it doesn't have to be just 2 numbers, if you have a whole string of numbers that you're multiplying, A times B times C times D times, I just lost my letters, A times B times C times D times E, whatever. Count the number of significant figures in each of those quantities. This one has 3, this one has 5, whatever the others are that you're multiplying. Whichever of those has the smallest number, the fewest number of significant figures, that will be the number of sig figs that you can keep in your answer. So this one has 3, this one has 5. 3 is the smallest out of 3 and 5, so we can only keep 3 sig figs in our answer. What I suggest that you do then is multiply your values out on your calculator, just keeping all of the digits that you have in there. Calculate them all together until the very last step, and when you're all done, then count up the number of significant figures in your final answer and keep those. So don't round it as you go along. Okay? All right, let's take a look at some more examples. I've written some examples here, and I've already put the answer that you get on your calculator already up there. So let's take a look. What is the final answer that we can actually write down for these quantities? Well, 3.0, how many sig figs does that have? Well, that 0 is to the right of the decimal. There is a decimal point present, so this has 2 sig figs. 5.158, that is 4 sig figs. How many sig figs can we keep? 2. 2 is smaller than 4. So what is this value if we only keep 2 sig figs? 1, 2, the value is 15. So there's the answer. We're not going to write approximately equal to 15 or anything like that, because the assumption is that the values that we have already are approximate values from measurements or calculations or whatever. So we will just write that as equals 15. You don't have to write this if you're actually doing the calculation. Just multiply it out on your calculator, keep 2 sig figs, and just write your answer as 15. 3.24 times 1.89763, 3.24, that's got 3 sig figs. 1, 2, 3, 4, 5, 6 sig figs. How many sig figs can we keep? 3. So what is this to 3 sig figs? 6.1. Now just notice this 8, that's a big number. It's 5 or larger. That's going to round this up. This is actually closer to 5 than it is to 4, or closer to 0.15 than it is to 0.14. So we're going to write this as 6.15. So that 8, we're going to round up the value of the 4. We're going to round that up to 5. Basically, when you have digits 0, 1, 2, 3, or 4, you will round these down. When you have digits 5, 6, 7, 8, 9, we're going to round those up. Some people say, well, if it's 5, that's right in the middle. Why would you round that one way or the other? Well, I would say that if you've got a digit of 5, say you've got a number like 6.15, that's only halfway in between 6.1 and 6.2 if the rest of the digits all the way out to infinity are 0. If this is anything other than zeros, then that really is closer to 6.2, and I would say that should round that up to 6.2. So just for a general rule, we'll say if the next digit is 0, 1, 2, 3, or 4, round the previous one down. If the next digit is 5, 6, 7, 8, or 9, round the previous one up. Okay? Now, the rule for division is exactly the same as the rule for multiplication. All we have to do is look at the number of sig figs. So in this case, 1.67 times 10 to the 3, that's got 3 sig figs. 3.2875, 1, 2, 3, 4, 5 sig figs. You multiply it out, or divide it out in this case, and we get this. We're going to keep 3. So what's the answer? Think about it. 1, 2, 3, that 9, we'll round that up, 5.08. Very good. Now, something I'd like you to start keeping in mind. Anytime you're doing a calculation or some kind of problem or something like that, when you get a final answer, I want you to ask yourself, does this answer make sense? Does it seem reasonable? Given what I've got, does this seem like a reasonable result? For example, we've got a number around 3, a number around 5. We would expect our answer to be around 15. Well, that's what we got. A number around 3, a number around 2 or 1. 3 times 2 is 6. Oh yeah, we got a number around 6. Let's look at this. We've got 1 over 3. That's a third. That's a number that's less than 1. We have 10 to the 3 over 10 to the 2. Now when you divide exponents, you subtract them. So this will be 10 to the 3 minus 2, or 10 to the 1, which is 10. So we've got a number that's less than 1 times 10, which is going to give us a number in the units place. And what do we end up with? Yeah, we have just a number of 5 in the units place. It's not 5 times 10 to the 3 or 5 times 10 to the minus 6 or something like that. It's in the ballpark of what we would expect. So if you can try and get into the habit of thinking about your answer, you will avoid many, many mistakes. If it doesn't agree with what you expect, go back and see, did you make a mistake? Or maybe what you were expecting is, you need to think about what you were expecting maybe a little bit more, and maybe you'll say, oh yeah, that is correct, or no, I made a mistake. All right, good. Now, I'd like to just point out one thing, something I like to show my students. Let me ask you a question. What is 3 times 4? Well, everyone wants to say 3 times 4 is 12, but in terms of significant figures, how many sig figs can we keep? 1 here, 1 here. Well, the answer is 10. 3 times 4 is 10. Now, that obviously sounds kind of funny, but keep in mind, if you're really talking about an approximate value of 3 that's somewhere in between 2.5 and 3.5, and an approximate value of 4 that's really between 3.5 and 4.5, then you really can't say that the answer is precisely 12. It's going to be approximately around there, and it actually varies around, and the best we could say, considering significant figures, is it's 10. So it's kind of funny, but it's the kind of things that we'll see with significant figures. Okay. We've looked at multiplication, division, the same rule as multiplication. Just count up the number of sig figs and the numbers you are dividing. And again, this is true. You could have a whole series of numbers multiplying in the numerator, a whole series of numbers multiplying in the denominator. All you do is count them all up. Count up the number of sig figs and each value that you have in there. Whichever has the fewest number of sig figs, that will be the number of sig figs in your answer. But what about addition? Addition and subtraction. The rule is not the same as multiplication and division. So let's take a look at that.